Our final slide here looks at some wave and sound applications. One of the first applications we're going to look at is called interference. So interference is when two waves collide. What they do is they don't bounce off each other. Like when we talked about particles, like two billiard balls. When two billiard balls collide, they bounce off each other. So that's a particle motion. That's what particles do. They don't interfere, they actually have collisions. Waves, however, interfere. So waves, when they collide, what happens is they pass through one another. Like if you're at the beach and a boat goes by and the wave from the boat mixes with the wave from the ocean and it creates a much larger wave. This is something we call constructive interference. So constructive interference occurs when two waves' amplitudes line up. So when the amplitudes or the peaks or the crests or the troughs, whatever you want to call them, when those things line up, they create a much larger wave. So if you look at the waves on the right, you can see the large wave growing until they're directly on top of each other. That is your point of maximum constructive interference. When the two waves double, the amplitude of one plus the amplitude of two equals two amplitudes. So you have a double wave. That's a constructive interference. Like if you have a rope and two people create a wave on either side of the rope, when the two waves meet each other, they create a big hump in the rope. That's constructive interference. Destructive interference is on the other end of the spectrum. When a crest and a trough line up with one another, they cancel each other out. This is known as destructive interference. So the wave then would flatline and you would have no wave. So if we were talking in terms of a sound wave, if you took a sound wave and the amplitude of the sound wave, the positive amplitude of the sound wave, and ran the negative amplitude at the exact same time, it would cancel out the sound waves. And that's what noise canceling headphones do. Noise canceling headphones actually receive the outside frequency and then they recreate the inverse of that frequency inside the headphones and play that noise at the exact same time. So those two frequencies cancel each other out, those two amplitudes. So what you have is you have no sound instead of a really loud sound. So that is how noise canceling headphones work, and they're pretty common today. They work really well for stuff like airplane noise, background noise, because that noise is staying at the same amplitude, same frequency. So it's very easy for those chips inside there to produce a destructive signal. One thing that DJs do and musicians do is they try to mix sounds and create beats. So they do this by actually using destructive and constructive interference, and as they play the two sounds over top of each other, it creates a beat based on where the alignment of the waves is. So you can see here a picture of a constructive and two different waves at different frequencies, F1 and F2, and when you combine those sounds, they're going to create constructive and destructive interference, and that's what creates the beat sound. The constructive would be the beat, and then you have a dead spot, then you have the beat. That is how you mix sounds to create beats. What DJs do when they have two turntables, right, and they're trying to mix sounds, back nowadays they just do it with digital, but if you have the two turntables, is they change the speed of the records so that the beats match up. The two records, if one beat is faster than the other one, they'll slow the first beat down as they're playing, as they're fading into that next record. So the beats match up, so it makes a seamless transition from one song to the next. When you have a wave, like a guitar string, it creates a standing wave. That's what creates that note or that frequency over a period of time. And a standing wave is a wave that repeats itself over and over again. Standing waves are easy to create, right? If you take two people on a rope and one person holds the end of the rope and the other person jostles the rope up and down, creating a transverse wave, you can create a standing wave on that rope. Standing waves are characterized by two things, nodes and antinodes. Nodes are the dead spot. You can see those represented by the blue dots there in the picture. That's the dead spot on the wave, and that is going to be the equilibrium position. And then you have the antinodes. Those would be the amplitudes. It's easy to remember because antinode and amplitude both start with A. You can see on the guitar, in the acoustic guitar, when you play the acoustic guitar in the body of the guitar, it creates standing waves. and these waves are where the sound comes out of. So you can see the dead spot, the white, the node, and you can see the black, the antinode in that picture. Here we have someone creating a standing wave against the wall with a rope. You can see the nodes and the antinodes. And what we're trying to talk about next is known as resonance. And resonance is the increase in amplitude of a wave because you force a vibration at the natural frequency of the wave. So the natural frequency is the wave or the vibration frequency that the object is going to give off when it's in its natural state. Like a child on a swing, the length of the swing and the child itself is going to create a natural frequency for that swing. That child is going to swing back and forth. And if you can time your push at the natural frequency of the swing, it's going to cause the swing to go to great heights. So what you want to do is you want to match your frequency to the swing's natural frequency, and that's going to cause resonance. It allows the child to go very high. If you mistime your push, like the child is coming towards you while you're pushing forward, you're going to cancel out the frequency. And you can see over here the guy with the rope, all he is doing is timing his hand movement with the frequency of the rope to create a nice large standing wave. This is a bridge in Tacoma, the Tacoma Narrows Bridge in Seattle, Washington. And what happened to this bridge is wind ripped across it, just like a reed instrument, and it caused it to vibrate. So the wind was at the natural frequency of the bridge, and it caused a great amount of resonance to occur in the bridge itself. So it created this wave on the bridge, and it actually ended up breaking. So that's one of the design flaws that engineers took into account when they make bridges now. We spoke of natural frequency, and what natural frequency is, this is the frequency that an object is going to vibrate at when it's struck. Everything has a natural frequency. Like if you take a glass, a wine glass, let's say, and you hit it with your finger, it's going to vibrate at its natural frequency, whatever that frequency is. If you take a rubber band and stretch it out between your fingers and strike it, it's going to go at its natural frequency. Guitar strings as well. That's why we tune guitar strings to the right length and the right tension to create the natural frequency in that guitar string so that when it's struck, it hits the right notes. The final wave characteristic that we're going to look at is known as the Doppler effect, and this occurs for all waves. So what happens with the Doppler effect is you can see below in the picture that there is a beacon sending out a signal, and we'll just say that's a sound wave being produced, and you can see, let's say that signal is moving from left to right, and as it moves, it is creating more the waves at the same frequency. So as it moves towards the right, the waves are arriving at the right-hand side of the picture faster than they're arriving at the left-hand side of the picture, even though it's being sent out at the same frequency. So because the object is moving towards it, as it sends out a new frequency, that frequency catches up to the old frequency that it sent out. So as it catches up, it creates a dramatic increase in frequency. And this, when we're talking about as it approaches, we shift to a higher frequency. We get a higher frequency sound. And as it goes away, you can see the waves are arriving less frequency, so you have a lower frequency. And this is known as the Doppler effect. And I got three examples to look at. First one is the fire truck. This is one we all can relate to. You're sitting there at a stoplight or something, and a fire truck's coming up on you, and you can hear it before you can see it, and as it approaches you, it gets louder and louder and louder and louder, and then immediately after it passes you, you can still see it, but you can barely hear it. So if you look at the fire truck at rest, it's sending out signals in all directions at the same frequency, but as it moves towards observer A in example B, you can see that those sound waves are arriving more frequently. And by the time it sent out a sound wave, it caught up to that one. So you're getting all of these sound waves at once. And then observer B is getting sound waves less frequently. So what happens with observer B is he can barely hear them because those waves get interfered with as they get to him, and they're not as strong. Doppler radar works in both a Doppler tower for predicting weather and in a speed trap gun or a speed gun. What happens is in the speed gun, it's going to send out a wave at a certain frequency. Let's say it's at 50 hertz. So it sends, well, it's going to be way higher than that, like 50 million hertz. So it sends it out at 50 million hertz. It hits the car and it comes back at 70 million hertz. The gun then can process the difference in frequency and find the velocity of the car very quickly. There's a very simple calculation you can do. So it sends out a frequency at 50 million hertz. It comes back at 70 million hertz. It can find the velocity of the car and know how fast that car is going. If you send it at a car that's moving away from you at 50 million hertz, it's going to come back at, let's say, 30 million hertz. That means the car is moving away from you at a certain frequency, or excuse me, a certain velocity. That change in frequency allows the radar gun to know your exact velocity. And since radar is a light wave and it travels at the speed of light, as soon as it hits you, it's back at the radar gun. So like less than a blink of an eye. So there's no way for you to slow your car down and get away from the radar gun. Same thing happens with Doppler radar for weather. The Doppler tower sends out signals in all directions, and that signal, it hits the atmosphere or the air, the clouds, let's say, in the atmosphere, and it sends back a signal to the tower. So it sends out a signal at a certain frequency, and then that signal is sent back to the tower at a different frequency than it was sent out. If it comes back at a higher frequency, it knows that the storm is moving towards the tower. If it comes back at less frequency, it knows that the storm is moving away from the tower. So it can take that difference in the frequency, find the velocity of the storm, and make better predictions of when that storm is going to hit certain areas. So if you watch big thunderstorms or if you watch Hurricane Tracker, they can predict where it's going to hit and when it's going to hit. Like if you're watching TV and there's a bad thunderstorm that comes on, let's say it's hitting Adams County at 7:10, it's hitting York County at 7:30, it's hitting Lancaster County at 7:50. Because as it moves to the different counties, or based on its velocity, they know when to predict it's going to be there. So that's why they use Doppler radar to help predict the weather.